This is going to be showing equivalency, and this is sensorial equivalency, but what we're looking at is an equilateral triangle and a rectangle. All we want to do is show that this is equivalent to this. And children can then choose to puzzle in. So now we can see that this was the same as this. And for the younger children that stops, but for the older children we can start to examine the length so that the base and the base, those are the same. And the height, well, the height is this length, which means that the height is half. You can see that it's the same. These are the same height, and this then is 2 times. So the rectangle is only half the height, but the bases are the same. And so with the older children, we can begin to formulate this into, it's the equivalent when the bases are the same and the rectangle is half the height of the triangle. Okay, well, what we want to do is show that this rhombus is equivalent to this rectangle. And as you can see, the heights are the same, the bases are the same, okay? So now the question is, can we puzzle this rhombus into this rectangle? And we can puzzle, it's the same thing, we can puzzle this in here. So now we've managed to say that these two are definitely equivalent. These two are equivalent. And this is going to be very important to show that these are equivalent for the next exercises. This is a very important concept, that this is equivalent to this. This will come up again later, so this is the first experience to go further into the sequence. Now, this is the one called the isosceles trapezium. Trapezium has 2 parallel sides and 2 sides that are equal, and a rectangle. And we want to show that this is equivalent to this. So again, children can then know that they can puzzle and find out that this is indeed equivalent. And of course, this can come in there just nicely. So now we can see that this is equivalent to this. And sensorially, that's all we need to know, that this rectangle is equivalent to this trapezium. However, if we're going to go further, we're going to look at some of the lengths. Now, what is the length of the base of the rectangle? It is this. It is the length of the major base and the minor base. So when we're calculating this, we have to do this side plus this side. These 2 sides together becomes the base of the rectangle. And then again, what is the height? Well, we can see quite clearly here, if we do it this way and this way, that it is indeed half the height of the trapezium. We can do it the same way as we did it with the other one, or we can see now it is half the height, okay? So a isosceles trapezium is equivalent to a rectangle when the base of the rectangle is the major base plus the minor base of the trapezium, and the height of the rectangle is half the height of the trapezium. This one here is going to see the equivalency of 3 different types of triangles, and they're going to look like this. We have the right angle, the obtuse angled, and the acute angled triangle. 3 different types of triangles, and these we want to prove that they are equivalent. Now remember, we proved that this rhombus was equivalent to this rectangle. And we can then see that the rhombus, that is the rhombus, and this is the rectangle, and this is equivalent. So now we've proved that this figure is equivalent to this figure, and this is the same as well. We can just show here that these can be moved in the same, so these are the same. These two are congruent, these two are equal. Okay, so let's move these back here. So now we have just proved here that these two are congruent, but all 3 of these are equal. So what we're saying here is that if we take half of each of these, we get these triangles. So these have to be equal. These have to be equivalent. However, when is it equivalent? So we want to look at it, is it any size? So we know that these are going to be equivalent. So it's half of this. That we know is true, but we have to prove how. So let's have a look at the bases. The base is all the same, okay? So the bases of each of these are the same. The base is equal. And what is the height? We see the height very clearly here. The height of this triangle is here. Here's the apex. And you remember the apex of the height, the altitude of this triangle is outside of it. And we can just push that up there. So we can see the height of this all 3 triangles is the same. So the 3 triangles are equivalent when the base is the same and the height is the same. This next exercise is to be able to show that polygons can be divided into triangles. So the first one we're going to look at is the pentagon. Now if we look, the pentagon has been split into 5 equilateral triangles, and it has gone from the center out to the radius. So we have a radius. And if we look here, we can see very clearly, or we can show it this way, that from the center and out to one of the vertices, that is now a triangle. And each of these triangles are congruent. So we're just showing here that a polygon, and in this case we have a pentagon, can be divided into that number, 5 sides. That means we can have 5 equal isosceles triangles, okay? Because we're going from the radius out to one of the corners. This can also be shown, this is for the regular polygons, and you can show it's regular by. This can also be shown using the decagon. We can see we have this, and this is now from the center out to each of the vertices. We now have isosceles triangles. And we can show that by showing it this way. From the center out to a vertices, we have isosceles triangles all the way around into 10, because there are 10 sides. Okay, so that is the first step of showing that any polygon, regular polygon, can be divided into isosceles triangles by making a line from the center out to the vertices of the sides. And any polygon can be divided into the same way. Now that we've shown that we can divide it into triangles, we want to have a look here and see. I want to show that, let's see, okay. We have this tray, and as you can see, it's split up into different triangles here. And we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 that are the same as these. And then we have 2 small ones out here on the sides. Okay. Now we want to prove that this is equivalent to this. This is what we're looking to prove here, that these two are indeed equivalent. Okay. So now what we can do is we know that these two are the same. And we can now show, if I remove this, I can start to puzzle these in. And now I can see that I have these two here, and obviously these come together and can make a single one here. So now I have shown that that is equivalent to this. And of course, this is what made up that piece there. So these two are equivalent. Now, what's interesting now is to show when I puzzle this back in, we're looking now at what about this rectangle is important. And you can see that the rectangle, the base of the rectangle, is equal to half of the perimeter of the full decagon. So it's only half here. That is the base of this rectangle. So if we were to add all those together, we'd get the base. Okay, so now what we're showing now, let's look at the height of this rectangle. The height of this rectangle is, and this is very important here, it is the apothem of this triangle. It is actually not the side, but it is now the height. So it's no longer the radius here. We're now dividing a triangle in two. Let's look at what this looks like. It is now this length here. That is the height of the triangle, of the rectangle. Do you see? So now you can see that is the height. So the height now is the length from the center out to the midpoint of the side. And in a polygon, this is called the apothem. And the apothem now is the height here. So we can calculate this by using half of the base will be half, and the height will be the apothem. That length from the center out to the midpoint of the side is now the height. So this is now the same. Now these will fill in up here, obviously. Possibly. So it is filling the full thing. We do see that the full tray, oopsie, the full tray, that's the one, just hold it there for me. The full tray is indeed the rectangle, and it is the polygon. So these two, you just made a shadow, these two are indeed equivalent when the base is half the polygon and the height is the length from the center out to the midpoint of a side, or the apothem. This is another way that we can show that how these two can be equivalent. Now, if you saw on here, we have this big rectangle and it's split in half this way, whereas this big rectangle is split in half this way. So we can say that these two are equivalent. So if this one and this one is equivalent, and this one and this one is equivalent, then this and this must be equivalent. Okay, so if we were to move these out of the way, then I could say that this is equivalent to this and is equivalent to this. All three of these are equivalent figures. Now I'd like to prove this. So let's bring our tray back from here. And now let's use just this frame here. Okay? So I want to prove that this, which is obviously the same as here, is equivalent to here. So if I remove this, then I can start to build with these pieces all around. And again, you're going to be able to see that I've just cut the height in half of those bigger triangles. Okay, so now we have that full around, and now these are all going to come and fit in here. As you can see, there's one little piece missing. That must be easy, so it's going to fit in here, and that would come over here. So now we can see that it is really, if I were to take these two out, I could fit one of these in. Okay, so these two are equivalent. And you can see that the height is half. So I've just split it in half this way and rearranged it a different way using these two pieces instead of using this piece. Yes, so the height is now half. Okay, so we have two different ways of showing that a polygon can be divided into, and it's equivalent to here. Again, if we then look, let's place this back over here. If we look at what makes the base of this triangle, this rectangle and this rectangle, let's look at the base. Now we're going to have the full perimeter. That is the full perimeter, and that is the base of this. Is the full perimeter. These need to be a little bit spaced. And then the height is now in half. Okay? It's half of the height here. So we know that multiplication is commutative. And therefore, we can say that it is the perimeter in half times the apothem, or the perimeter times half of the apothem. So we have the full perimeter times half of that height, or we have okay, so this one is half of the perimeter times the full height, the full apothem, or we have the full perimeter times half of the apothem. So it is the perimeter times the apothem divided by 2. And that is how you would find the area of any polygon.